Hi, welcome to the Cosmic Busker. My name is Bobby Cody. In this video I want to respond to a comment that came in on my Ancient Mars Civilization video. The commenter left a comment, post it right up here so you can see it. I'm also going to give you a link real quick to the Ancient Mars Civilization video. It's a 5-part series I did on Ancient Mars Civilizations. I'll post the link to the one in which this comment came through. Although I think the user ultimately deleted the comment. I can't find the comment. It came through on my notifications. I couldn't find the comment on the article itself. Maybe it'll appear there all of a sudden. Didn't go to spam or anything. But I still want to respond to it. And I'm going to also notify the YouTube user who made that comment that I'm responding to it, because it's important. If you're skeptical, ask a question. I'll answer your question to the best of my ability. So let's take a look at his comment in question. POWwolf Rider commented on my Ancient Mars Civilization Timeline and Discovery video. The comment went, "Where do I look up the math for higher dimensions planet wobble? You had my attention until then." Well, POWwolf Rider, I will do my best to answer that question within the boundaries of my layman education and self-education. But it's based on the work of scientists and physicists and higher mathematicians that I'm going to point you to. So the first answer is, it's going to be a complicated answer. First I'm going to answer with higher dimensions. We exist in a 4-dimensional universe that we can perceive. Length, width, height, time. 4 dimensions. So then the next theoretical dimension would be the 5th dimension. 5 dimensions. Now, the first physicists that I'm aware of that worked in 5 dimensions, mathematicians did it. I'm going to get to the mathematician who was just brilliant and worked in higher dimensions, and his work was so far ahead of everybody else that it is, he was 1800s, and his work is still being utilized by physicists. I'll get to him in a moment. But the first physicists to work in higher dimensions successfully that I am aware of were Kaluza and Klein. I don't remember their first names off the top of my head, but their theory was called the Kaluza Klein theory. I'll get some links and I'll post down below to the Kaluza Klein theory. But essentially, the summary of the Kaluza Klein theory is that light, sunlight, the lights that come from the light bulbs and all the lights around, there's light around you at all times, otherwise you would not be able to see. In perfect darkness you couldn't see. Our eyes analyze light, take in light. So light comes from a vibration of the 5th dimension. The big question now, light, there's a lot of mysteries around light and why light and how strange light is compared to everything else that we perceive as reality around us. Kaluza Klein said light is a vibration of the 5th dimension. So now, that was their theory. Einstein proved it later. A summary of how Einstein proved it. Well, he basically said that in his general relativity, he said that if light is a vibration of the 5th dimension, as they hypothesize and as my general relativity incorporates, then light traveling through the gravity of the sun or affected by any gravity whatsoever will bend. Ultimately, they proved this to be true. Once we had the ability to see a star going across the event horizon or horizon of the sun and going through the gravity, and we could see that sun's light hitting the gravity of the sun, we saw it bend. Star shifted position all of a sudden because its light was bending. So Kaluza Klein's theory was proven to be true, which means there's a fifth dimension. Okay, so now the next step in answering your question is to take a look at five-dimensional space. And in particular, you asked me about this higher dimensional stuff in a planetary wobble. Okay, so what we're going to do is we're going to look at five-dimensional space, and we're going to look at a sphere in five-dimensional space. So right now I'm going to take you real quick over to Wikipedia five-dimensional space webpage, and we'll take a look at what they have up on there. I'm not particularly concerned at this point with the information on there. I just want you to see the picture they have of five-dimensional space, because they have a picture of a sphere. Let's take a look at it. Here we have in front of us a 2D orthogonal representation of a 5D sphere, courtesy of Wikipedia. Okay, so there we have a representation of a 5D sphere. It's hard because we're in 4D and we're actually doing it on paper or camera, which is 2D. Suffice it to say, we can use our mind's eye to picture what that looks like in 4D as if it was a rotation sphere in front of us. So that's what we're going to do. You can see that up there, or up there. It's one of those corners, I always get confused. If it's rotating, it starts this 5D sphere starts to have a motion like this, okay? And that motion, it's like any type of motion. Motion is a form of energy and creates energy. If I go like this, I move wind. You know, windmills operate off of that. Any type of motion creates energy. So the sphere rotating in higher dimensions, again, take a look at it, you can imagine those corners and the going in and out, that creates energy within the sphere. Now, I used a 5D representation because that's the next level up from us. We're in 4D, that's what 5D looks like. That's a 5D representation so that we can try to understand it. It gets very difficult. Now I'm going to post a 60. There's 60 as well. There's a 60 representation. Once again, you can imagine it rotating and moving. What I'm going to do now is I'm going to cut to two different examples that people give of spheres rotating in higher dimensions. There's different ways to represent this because it's difficult to represent higher dimensions in our 4D reality. But I want to again give you an example of that rotation, and you can see the movement that it creates. You'll see different shapes moving, etc., etc., and that movement creates energy. Ultimately, I'll get to the point where I show you the math or where you can find the math, but I want to give a background so people see that there's a long, long history of good math and physics and science behind this. So let's go to the sphere representations of a sphere rotating and how that looks in our 4D, how we would represent that in our 4D. Let's cut to that right now. Okay, here we have one example of how we would perceive a hyperdimensionally rotating sphere. Now you can see the way all these shapes change, etc. One way that you can view this is energy movements on the surface of the sphere as well. And ultimately those energy movements can be represented by math as well, which we're going to show in a short while. So now I just want to take a look at one more representation of a video of hyperdimensional spheres rotating and how that can be perceived. Because as I stated, there's multiple ways this can be represented, but I just want to give you a couple of examples before we move on to how this gets into reality and the mathematics behind it. Here we have another representation. You can see all the internal movement. That internal movement represents energy. Okay, so now I showed you how a hyperdimensional sphere or a hypersphere rotating can be somewhat represented in our 4D reality. I want to take a look at the mathematics behind hyperdimensions and spheres, because once we understand the higher mathematics between pertaining to hyperspheres and how that relates with reality and what we found in physics, I think you'll have a general understanding of why I could state what I stated. So first I'm going to cut to two different videos. I'm going to put them up, one right after the other. I'm not going to make any comments because I want you to see the two videos are basically restating the same thing. It has to do with 10 dimensions and what happens at 10 dimensions, because at 10 dimensions something magical happens. And then we'll cut over to the mathematician who changed everything. So let's cut to those two videos. We'll look at them real quick, maybe a minute or two on each video, and then I'll come back and tie everything together.
Now, let's try the whole thing in 3D. Start with a cube and split it into 8 equal parts, or octants. Place a sphere so that it perfectly nestles inside each octant. In the center of the whole cube, draw a sphere so that it touches each of the other 8 spheres. Again, this sphere is way inside the cube. We can repeat the same thing in higher dimensions, nestling 2 to the n equal-sized spheres into an n-dimensional cube, and constructing a central sphere that touches the others. The central sphere gets bigger as the dimension goes up. But here's the totally mind-blowing part. At 9 dimensions, the central sphere touches the sides of the cube. After 9 dimensions, the sphere actually bursts through the sides of the box. Why is this happening? Roughly because as the dimension goes up, the distance between opposing faces of the cube stays the same, while the diagonal distance between opposite corners gets longer and longer. See? Hyperspheres are totally counterintuitive.
We've already done the first couple. In 2D, it was 0.41421. 3D, which we just did, 0.7320. 4D, it's still the square of 1, square of 1, square of 1, square of 1 for the fourth direction. Add them together, take the square root, which is 2. That's nice and straightforward. So in fact, the radius of the central sphere in 4D is root 4, which is 2, minus 1, which is 1. So now the middle sphere has exactly the same radius as the padding spheres around it. So there will be 16 padding spheres in 4D, and the single one in the middle is exactly the same size.
That's awesome.
It's pretty cool. 4D, lovely stuff happens. 5D, let's see what happens. You've now got 32 padding spheres. The box is 4 in all of 5 different directions, and the middle one has a radius of 1.2360. So now it's bigger. The middle one is bigger than the other ones around it. That's odd. Let's keep going. In 6 dimensions, it is 1.4494. Bunch of stuff, a little bit bigger again, but hopefully slowing down. 7 dimensions, 1.6457. 8 dimensions, 1.8284. 9 dimensions, it's 2. So in 9D, the middle sphere has the same radius as the distance from its center to the outside of the containing box. So in 9D, the middle sphere has just contacted the outer surface of the box. It's somehow got past the padding spheres, which are all over it. It's got through them, even though it's limited by them, like they define how big it is.
It's not allowed to touch them.
It's not. It kisses them. It doesn't. It's not going through them. Somehow, it's big enough that it's contacting the box without going through the spheres, touching it. And in 10D, slightly disturbingly, it escapes the box completely. It's now 2.162. So as of 10 dimensions, and indeed 10 dimensions onwards, it is bigger than the original box which was containing it. I mean, the short moral of the story is that higher dimensional spheres are really weird and difficult to contain.
How are you reconciling this in your head? How does it make sense to you?
There's a trick you can use in mathematics called not worrying about it. Everything we have learnt no longer really works. And so people who do have to come to grips with higher dimensional spheres will describe them as being spiky. Higher dimensional spheres are spiky.
Okay, so now I've taken us to 10 dimensions. 10 dimensions, as you can see from these past two videos, something very strange and counterintuitive happens. A sphere that is supposed to be encapsulated by a box all of a sudden, for some reason, is larger than the box than it can be encapsulated by. There's something very counterintuitive and strange about this, and it goes to part of the work by an 1800s brilliant Asian Indian mathematician. Srinivasa Ramanujan was his name. I believe that's how you pronounce it. This guy was hundreds of years, his 1800s, he was a couple hundred years ahead of everybody. He just invented his own mathematics, and it was brilliant. Quantum physicists and higher order mathematicians are still referencing his work because in a short amount of time, he died in his 20s, but by the time he passed away, he had just completely revolutionized all types of mathematics, such that for decades and decades we're still looking at his work and just marveling at it. So the short answer I have for you then, POWwolf Rider, is to go get some higher dimensional texts and take a look at the work of Ramanujan. But I'm going to summarize essentially here how that correlates with what we know and why we know that this is true with the higher dimensional sphere rotating, etc. Ramanujan, came across this 10 dimensions as well in his work, and it had to do with functions. I'm going to take a look at a real quick quote from Wikipedia, but it has to do with string theory. Right now, physicists in trying to understand the quantum world and unify physics from the quantum world to the larger world. Quantum is small, and then we have the larger world around us. They're trying to unify the mathematics or the physics between the two. They've used string theory as part of it. And string theory, one of the reasons Ramanujan back in the 1800s is so amazing is because it's his functions that he created back in the 1800s that quantum physicists need now. He essentially discovered string theory back in the 1800s before we even had the science, Ramanujan did, before we even had the science to test it and understand it. So these physicists are using Ramanujan's work, and in order for these strings in string theory to be able to create the universe around us in the quantum world, it has to be 10-dimensional. So I'm going to cut to a quick quote right now, and then I'll come back and I will finish it up. These are precisely the mathematical identities discovered by Ramanujan. This is back in the 1800s. The string vibrates in 10 dimensions because it requires generalized Ramanujan functions in order to remain self-consistent. So basically, now physicists are beginning to understand that in order to understand our reality, they have to assume that we live in at least a 10-dimensional universe. Once they put all the equations and everything into a 10-dimensional universe, everything starts to make sense, and they're able to make sense of the numbers and the equations, etc. That's why string theory works. So, to answer your question, POWwolf Rider, once they put a 10-dimensional take a sphere, it's rotating, and they presume that it's at least in 10 dimensions. As I showed you, in 10 dimensions, all of a sudden something strange happens. A sphere inside of a cube is bigger than the cube that encapsulates it. But it's still supposed to be encapsulated inside. How can it be bigger and still inside? That's where you start to understand why you get energy coming out at the lower dimensions. If you can visualize this. Again, so to point you to the math, I would point you again back to the video where it shows you what happens at 10 dimensions with the sphere. If you want the very high order math, I would point you to Srinivasa Ramanujan. It'll take you probably a couple decades. Get some textbooks on him, understand his functions, read up on everything that he's done, and all the algorithms and everything, and eventually you'll be able to comprehend it. The shorter way is to take the work of experts, read the work of experts, try to understand what they're saying and where they're pointing. So that is a very short answer to you, POWwolf Rider. I did my best. That's all. If you have any comments, pro or con, I'd love to hear them. I have no issue with any negative comments as long as they're productive. Appropriate questions and appropriate criticism only makes us better. So thanks for watching. Everybody have a great day.